OpenAI's Sora can simulate a robot lifting a box in perfect 4000K resolution. But if you tried to plug that video directly into a real robot arm, the machine would drop it or break its own joints. The gap isn't in the AI vision, but in the hardware ability to feel and react. This brief exposes why high-fidelity generative video fails as a direct control signal for physical systems, because the missing link is haptic feedback force data and mechanical latency, creating an insurmountable sim-to-real barrier that no amount of visual fidelity can bridge on its own. We often hear headlines suggesting that if we build better vision models, robots will instantly master manipulation tasks. The assumption is simple: solve seeing equals solving doing. But this conflates two fundamentally different layers of intelligence in embodied systems. A robot does not just need to see what a box looks like, it needs to know how much force to apply without crushing the cardboard or slipping when friction changes. Generative video models like Sora are designed for screens, producing pixels that look real but contain zero information about weight, texture, resistance, or torque. When you feed this stream into a control loop intended for mechanical actuators, the system is effectively blind to the physical reality it must navigate. Consider what happens when a robot attempts to grasp an object based solely on Sora's generated sequence. The video predicts smooth motion and perfect contact points because digital simulations assume ideal conditions without friction or inertia. In the real world, however, every surface has microscopic roughness that affects grip, and every motor has mechanical backlash that creates delay between command and movement. A robot relying only on visual prediction will apply torque based on a pixel-perfect simulation rather than actual resistance. It might push too hard until it deforms an object or not enough to lift it at all, because the system cannot detect slip in real time. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This disconnect highlights three specific technical bottlenecks where visual generation fails to translate into mechanical action. The first is the absolute absence of haptic feedback. Current generative video models output pixels, not force vectors. A robot simply watching a generated frame has no way to gauge if an object is slipping or too heavy before it applies torque. Without tactile data from force and touch sensors, the system lacks the critical loop required for safe manipulation. It cannot distinguish between lifting a light foam block and a dense metal weight because both might look identical in a high-fidelity video stream until physical contact fails. The second bottleneck is mechanical latency, which creates instability in closed-loop control systems, where millisecond delays result in collisions or structural damage. Sora generates frames based on predicted physics, but real-world actuators have inertia and response times that do not match the instantaneous nature of video playback. When a robot tries to correct its trajectory based on visual feedback, there is always a lag between seeing an error and moving the motors to fix it. In high-speed tasks or when handling heavy loads, this delay compounds, rapidly causing oscillations that can lead to catastrophic failure if the control software does not account for physical inertia. The third issue is the sim-to-real gap, which experts like Jonathan Hurst from Agility Robotics and Hans-Peter Bronmo, who worked at Google X, have noted as a decades-long challenge rather than an algorithmic fix. Digital simulations cannot perfectly replicate the chaotic physics of the real world without sensor data because they are essentially predictions of what should happen, not commands for handling physical resistance in unstructured environments. A generated video is just that, a prediction, and it lacks the multimodal reasoning required for robotics policy layers such as grasp planning or trajectory adjustment when conditions deviate from the script. Research presented at ACM Chai 2024 confirms these limitations while analyzing public discourse around generative models. The study involved 7 authors, including Reza Hadi Mogavi, Derek Wang, Joseph Tu, Hilda Hadan, Sabrina A. Eskandura, Pan Hui, and Lennart E. Naki, who examined over 1,827 Reddit comments across 5 specific subreddits focused on technology and artificial intelligence. Their analysis of the initial PDF submission, which was only 89 kilobytes in size, revealed that while users focus on Sora's visual capabilities, they overlook the fundamental engineering constraints preventing deployment in physical systems. The public discourse often treats these models as complete solutions for autonomy, But the technical reality is far more nuanced. Visual generation does not inherently encode force dynamics, meaning the actuator bottleneck remains unsolved by video alone. We are seeing a mismatch where software teams celebrate better visual fidelity while hardware engineers struggle with the same fundamental problem of sensing resistance and reacting within milliseconds to prevent damage. This gap explains why we have yet to see humanoid robots running marathons or performing complex assembly tasks despite having powerful video models that can describe them perfectly in text or show them flawlessly on screen. Understanding this distinction reframes how we should view AI progress in physical systems. It clarifies that mastering seeing is not the same as mastering doing, and highlights that the future of embodied AI requires integrating force sensors, haptics, and low-latency control loops rather than just better cameras or larger language models. We are still building the nervous system for these machines to match their visual cortexes, meaning progress will come from combining high-fidelity vision with robust tactile feedback and mechanical intelligence, not from video generation alone. The path forward involves recognizing that foundation layers of perception must be supported by intermediate policy planning and finally actuator control where force dynamics dominate over visual appearance. Until we can bridge the gap between pixel-perfect simulation and physical resistance, generative video will remain a powerful tool for entertainment and marketing, but not a direct controller for the machines shaping our physical world. The engineering reality is that intelligence in robotics comes from sensing what happens as much as predicting it happening. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.